that I am not an expert on electrochemical impedance spectroscopy. I know a little bit about it, and we practice it in the lab. And a basic understanding of electrochemical impedance spectroscopy is really critical to be able to interpret results and understand what it's telling you. Okay, so we're going to start simply and develop some simple equivalent circuit models of cells and try to understand where they come from. So the first thing that I want to talk about is what happens in lithium-ion cells as they undergo extended charge-discharge cycling. Okay, so here I'm showing some data for capacity of a small pouch cell versus cycle number for cells tested at 40 degrees C and cells tested at 20 degrees C. C over 3 volts to 4.3 volts, 3 volts to 4.3 volts. And there's two sets of data here. Blue is called original, and red is called improved. And if you look at the capacity versus cycle count curves, the red shows much less capacity fade than the blue. And there's this other thing that's being plotted here called delta V, all right? So I want to talk to you about what is this delta V thing and how should you think of it in the absolute simplest way. So that's what I'm going to do first, and I'm going to go to my document camera for that. So if you have a lithium-ion cell, we know its voltage versus stated charge curve is a sloping curve. Maybe it looks like that. Let's say this is measured under incredibly slow conditions like C over 1000. At such a slow rate, you're very near equilibrium. And what you measure during discharge and what you measure during charge going back again will be virtually the same. But if you measure this thing at a higher current, what you'll learn is the voltage during discharge shifts down a bit. So maybe this is C over 2 or something. And the voltage during charge shifts up a bit. And, you know, when you take science in grade 8 or first year physics, we model a battery as an ideal cell with an internal resistance in series. And if you pass a current through this thing and you want to know what the terminal voltage is across the terminals, V will be equal to V naught plus or minus IR, depending on which direction the current flows. And this R is called the internal resistance in the simplest treatment. Now, when I teach first year physics, I often get asked by students, well, why do you guys put an internal resistance into a battery? They're thinking that we actually put a resistor in there. And of course we don't. This internal resistance represents the losses that occur due to diffusion of lithium ions in the electrolyte, diffusion of lithium ions in the electrode particles, the finite resistivity of the current collectors and the carbon black and the electrode particles, all those things lumped together to give you this internal resistance. So the voltage is offset from equilibrium by this amount, IR, which is this in the diagram, IR. So this difference between charge and discharge, that's what we call delta V. And is approximately twice the current that's being applied times the internal resistance of the cell, whatever its origin might be. And when you look at these curves, which will go back now to the PowerPoint, when you look at these curves here, you'll see this delta V is increasing with cycle number dramatically for the blue and not so much for the red. This is 3,000 cycles, which at C/3 is 2 years of testing. And this means the internal resistance of the cell is increasing, whatever its origin, okay? You know, is it charge transfer resistances at the electrode surfaces? That means a lithium ion has to move from the electrolyte through whatever SEI layer may be present on the electrode and into the material where it can combine with an electron and intercalate. That's a charge transfer resistance. Maybe that's increasing if the thickness of the SEI thickens during testing. Or maybe you're losing electrolyte salt as the cell cycles and the ionic resistance of the electrolyte is becoming larger. You know, you don't know the origin of this increase in internal resistance or internal impedance, but you can see it's increasing, right? And it's bad. You don't want it to increase. So the real reason that we do impedance spectroscopy is to try to figure out the origin of this increase in impedance, to separate the components separate various components that might be causing this. And the reason that impedance spectroscopy can do this is because each of these different processes, transport of lithium ions through the solid electrolyte interface, or transport of ions through the electrolyte, or solid state diffusion, they all have a different signature if you measure impedance as a function of frequency. So here in these experiments, we're learning about the internal impedance of the cell from direct current measurements, not from alternating current measurements. So impedance spectroscopy involves applying an alternating voltage to the cell and measuring the response at the same frequency. Okay, so any questions about this? It's really important to understand why we do electrochemical impedance spectroscopy. It's not like we do it for the fun of it. We do it to try to learn, you know, where the limitations in a electrochemical cell are coming from. So if you take a look at a electrode in a lithium ion cell, so here's the current collector. You know, positive electrode particles are about 10 to 15 microns in diameter. The total thickness of the positive electrode layer is 50 or 60 microns. So it's only 5 or 6 particles deep, okay? You know, so this is just a slice through the positive or negative electrode, just showing one stack of particles 5 deep, right? And then you've got carbon black indicated by these black chain-like segments here. The whole electrode is filled with electrolyte, which is the white material. There's an SEI layer on the surface, which is indicated by this color that could be red or orange. I can't tell the difference. Might even be green. And the lithium ions in the electrolyte can diffuse along. Electrons can travel through the carbon black to the particles, or maybe if the particles touch, they can go particle to particle. The other electrode is over on the right. You know, so you want to make some kind of a model for this electrode, which represents the way it would behave if the cell were subjected to an alternating current signal. Okay, so you make what's called an equivalent circuit for the electrode, and this is what we see above is a transmission line model for the electrode. So let's talk about it. So these resistors down at the bottom, this bottom row, represent the electronic path through the carbon black to the particle. And then at this point, it is possible for the electron to go into the particle and combine with a lithium ion, which is coming through the ionic path of the electrolyte, and has to go past 1, 2, 3, 4 to the 5th particle. So it moves quite a ways through the electrolyte, lots of ionic resistance. And it gets there and it combines with the electron by passing through. The ion has to pass through this solid electrolyte interface layer. And the solid electrolyte interface layer is modeled by this resistor capacitor parallel circuit. So the electrons and the ions can combine and intercalate into the particle. And they can do it in the particle at the back, the next particle, then the electrons have to travel further, the ions don't have to travel quite as far, and so on. Okay. So this is a one-dimensional transmission line model of a real electrode. And things can be more complicated than this. This is kind of like the simplest thing that you could ever imagine. And we will simplify even further than this in our discussions. Okay, so any questions about this, what you see here?
So, quick question, maybe clarification. Each node in this circuit is not a site, but a place that lithium and an electron can combine. Am I understanding that correctly?
No.
Okay.
What happens is if you cut the resistor capacitor circuits down the middle, the way my mouse is moving, everything that transport above that is ions, and everything that transport below that is electrons.
That helped my understanding. Thank you.
Yeah. Oh, I forgot to tell you what this vertical resistor is. This represents a contact resistance between the carbon black and the particle surface. It may or may not exist, and it may also have a series capacitor in parallel with it, it turns out. Okay, any other questions about this thing?
Yeah, good question, Jeff.
Yeah.
So for the transmission line model, so are we just modeling like each separate particles and compared to like doing same measurement as a bulk, I guess. So is it common to, do these studies we'll be using the transmission line model, or will the bulk will be okay as well?
Well, the problem with transition line models is they're not easy to solve for the average human on a piece of paper quickly. So what we do is we make approximations. Lots of people have treated impedance spectroscopy from electrodes with transmission line models. In our lab, Dan Abarbanel was the last person to do that. If you take a look at his papers, you can appreciate what he did. But generally, you can understand the basics of what's going on in a lithium-ion cell without having to resort to the complexity of a transmission line model.
Cool, thanks.
Yeah. So let's simplify things a lot. And Alison Keefe's master's thesis really is a very good place to go and read about impedance spectroscopy. Her whole thesis is more or less about impedance spectroscopy, and it's very well done. So the idea then is you have ions in the electrolyte, and there's some solution resistance associated with their transport through the electrolyte. And then they come to a solid electrolyte interface on the surface of each electrode particle. And that SEI becomes electrically charged. There's an electrical double layer that builds up across this interface. It's not an electronic conductor. So you can have charge buildup across this interface. You can also transport the ion through the interface to combine with an electron and then intercalate into the material. So there can be direct current transport through this interface. So this equivalent circuit is what people often use to represent an SEI layer, where you have the path that the ions can diffuse through the SEI represented by this resistor, and the fact that you have an electrified interface represented by this capacitor. So it's a resistor capacitor in series that you use to represent the SEI. And then over at the contact between the electrode particle and the current collector, there can be another electrified interface there. Generally, the resistance of this interface is much smaller than the resistance of this interface, but you can still have charge buildup there. And this is called the contact interface. Okay, so often you would have one RC circuit to represent the solid electrolyte interface, and a second RC circuit to represent the contact between the current collector and the electrode material. Okay, so any questions about this? So what do we do in impedance spectroscopy? Well, we generally take a 10 millivolt peak-to-peak signal, AC signal, and apply it to a cell at equilibrium. So the cell might be at 50% state of charge, for example. And then you measure the current that flows to or from the cell due to this, if you like, rapid charge and discharge over a very narrow range. So if you excite with 10 hertz, for example, you'll measure a current signal also at 10 hertz. And you do this for many, many frequencies. So a typical impedance spectrum might start at 100 kilohertz and go down to 10 millihertz, for example. And you would measure about 10 points for every decade of frequencies. So that means between 100 kilohertz and 10 kilohertz, you would measure 10 frequencies. And between 10 kilohertz and 1 kilohertz, you would measure 10 frequencies, and so on. And then to get the impedance of the cell, well, the ratio of the voltage to the current is the impedance. So if you measure the voltage, if you apply the voltage and measure the current, and you take voltage over current, you get the impedance. What should confuse you, perhaps, is well, this is some kind of sine or cosine wave, and this is also some kind of sine or cosine wave. So how do you divide voltage by current in such a situation? And that's what I want to spend time on now. Okay, any questions about that?
So Jeff, question, the EIS technique, is it done at a particular state of charge?
You can do it at any state of charge you like of a cell, and you will find that the impedance characteristics of a cell vary with the state of charge. So it's very important to, always measure at the same state of charge if you're trying to figure out what's happening to a cell over its lifetime. And generally we would measure ourselves here, we like to measure at 100% state of charge and at 50% state of charge. Those are two good state of charges that characterize the cell quite well. Okay, so it says derive the impedance of a resistor, derive the impedance of a capacitor, so on and so forth. So we're going to do that, okay? We're going to do all this stuff that it says here. So derive the impedance of an RC parallel circuit, derive impedance of an RC parallel circuit in series with a series resistor, blah, blah, blah. And we're going to go to the document camera to do this. I think you can see the document camera, right?
No,
Really?
still the presentation.
How about now?
Yep, there you go.
Okay, good. Okay, so a resistor is really simple. So a resistor obeys Ohm's law, which says V equals
Hey Jeff,
IR.
can you please? Thank you.
Is that better?
Yeah.
Yeah. Or V equals IZ. That's for a resistor. In fact, this is always true. This is Ohm's law here. So for a resistor, the impedance of a resistor is just R. Okay, that's for a resistor. Now we're supposed to do a capacitor. Well, capacitor is more complicated. Okay, so what we're going to do is we're going to do exactly what we said we were going to do. We're going to apply a voltage, which is an AC signal. V equals V naught. Okay, now if we want an AC signal, we could say cosine omega t, or we could say sine omega t. But all the mathematical manipulations are very cumbersome if you use sines and cosines. So we use complex numbers instead. E to the I omega t. Now what the hell does this mean? So if you haven't done AC circuits in complex number notation, you'll be saying, what the hell does this mean? Okay, so what you have to do is take the real part to get physical meaning. And you have to know that e to the I theta is equal to cosine theta plus I sine theta. So that means e to the I omega t equals cosine omega t plus I sine omega t. I hope everyone knows that I is equal to the square root of -1. If you take the real part of this, that's just cosine omega t, okay? So you can represent sines and cosines with complex numbers, provided you realize that you're taking the real part to get physical meaning, okay? So then a capacitor, the charge on a capacitor is equal to the capacitance times the voltage. That's what a capacitor is. So if you increase the voltage, you increase the charge linearly, and the proportionality constant is what we call the capacitance. So that means dq by dt, the derivative of charge with respect to time is the current in a circuit. So that will be equal to C times dV dt. And we have an expression for voltage up here, which we're going to put in there. And the derivative is going to be V naught I omega e to the I omega t. And then the impedance, Z, is the voltage divided by the current. Well, we have a voltage, and now we have a current. So it's V naught e to the I omega t over C V naught I omega e to the I omega t. And a lot of this stuff all cancels out, as you can see, and you get 1 over I omega c. And that is the impedance of a capacitor. So it depends on the frequency. When the frequency is incredibly large, a capacitor behaves like a short circuit. The impedance goes to 0. And when the frequency is 0, a capacitor acts like an open circuit. This thing, the magnitude of this thing becomes infinity when omega is 0. Okay, so are there any questions about that? All right, good. I'll scan these notes and send them to you after. Now our PowerPoint said we were going to do what is the impedance of a parallel RC circuit. So here we have a resistor and a capacitor in parallel, and we want to know the impedance of this thing. Well, if you have parallel connected circuit elements, then 1 over Z is 1 over Z1 plus 1 over Z2 for parallel. Okay, so that means 1 over Z we have we have R, and the impedance of a resistor is R. It's 1 over R. And then we have a capacitor, and the impedance of a capacitor is 1 over I omega C, right? So Z2 is 1 over I omega C, and we need 1 over that, so it's I omega C. All right. So that means Z is 1 over all of this junk. And we really want to separate this into the real and the imaginary part. So we're going to do that. And in order to do that as cleanly as possible, it's useful to multiply top and bottom through by the resistance. And then, if you want to convert this to real and imaginary parts, you multiply it by you want to get the imaginary stuff out of the denominator. So to do that, you multiply top and bottom by complex conjugate of the denominator, which is 1 minus I omega RC over 1 minus I omega RC. So I've just multiplied by 1 here. And then if you do the product, you get Z equals R minus I omega R squared C. And the two bottom components gives you 1 plus omega squared R squared C squared. And that is the impedance of a parallel RC circuit as a function of frequency. So it has a real part, which I'll circle in black. That's the real part. And it has an imaginary part that I'll circle in red. And an impedance spectrum is generally a plot of the imaginary part versus the real part at all the different frequencies. I'll show you some impedance spectra in a second. So you need to know the real part and the imaginary part of the impedance to plot a normal impedance spectrum. Okay, so are there any questions about this?
Yeah, quick one, Jeff.
Yeah.
How do we interpret the imaginary part of an impedance? Because earlier you said, to get the physical meaning, you take the real part.
The imaginary part of the impedance is what happens. The easiest way to answer this is if you look at the current in response to the applied sinusoidal voltage. If you're talking about a resistor, the current and the voltage are exactly in phase. So it means the current response is a maximum when the voltage signal is a maximum. And the current response is a minimum when the voltage stimulus is a minimum. But if you have a capacitor, what you learn there is that there's a phase shift between the voltage stimulus and the current response. and it's 90 degrees. So when the voltage is a maximum, the current is no longer a maximum. It's 0. And when the voltage is a minimum, the current is either a positive maximum or a negative maximum. Okay. So the imaginary part represents the portion of the response that's phase shifted by 90 degrees relative to the part that is not phase shifted at all. I don't know if that's helpful.
It is, thanks.
All right, so I'm going to go back to my PowerPoint now. Where is it? No. Maybe it's this. I don't know where it is. What can you guys see now? Do you see a PowerPoint?
Yep.
Yep.
Really? Does it say derive impedance of a resistor? Use Ohm's law?
Correct.
Okay, great. I have no idea how we got here. All right, so then it says derive impedance of an RC parallel circuit in series with a series resistor. We'll come to that in a second. Okay, so here are some simple models of what you could use to represent the impedance spectrum of components of lithium-ion cells. So for example, this would be a positive electrode in the electrolyte. You have a charge transfer resistance at the surface to the positive electrode. You have the solution resistance to get the ions to the positive electrode, and you have the electronic resistance to get the electrons to the positive electrode. Now you might say maybe the electronic resistance should be over on the left side of the circuit. The electrons come from the current collector, the ions come from the electrolyte, but it turns out it doesn't matter where you put series connected circuit elements. Just from the point of view of understanding, it would be more convenient to put the electronic resistance over on the left. It doesn't change what the impedance of this combination is. So series connected elements just add. So you have the solution resistance plus the electronic resistance, and then the impedance of this parallel RC network, RC parallel combination. And this is exactly what I wrote on my piece of paper for the real part and the imaginary part. And then you might want to think about a full model for a lithium-ion cell, you know, where you have represent a positive electrode and a negative electrode. Well, then you end up with a solution resistance and electronic path resistance that would represent electronic conductivity in both electrodes just lumped together because series elements add together. And then the two RC circuit impedances together. Okay, so not very complicated. Any questions about this? All right, so now it's time to take a look at some real spectra and compare to calculations that we can make. All right. So these are impedance spectra, and what they are is a plot of the imaginary part of the impedance. This is measured, by the way. versus the real part of the impedance at a whole bunch of frequencies from 100 kilohertz down to 10 millihertz. And Allison here has indicated where each of the frequencies correspond to each decade are located, all right? And this is, the vertical axis is the negative imaginary impedance because a capacitive impedance is negative. You see all these things that come from the capacitor part of a parallel RC circuit, they're negative. So just so the impedance spectrum is not upside down, you plot the negative of this thing. Okay. So I need to explain to you what type of a cell is being measured in this case, and there's two particular traces shown. One is for something what's called a blocking electrode cell, the red, and the other is for a non-blocking electrode cell. I'll talk about that in a minute. The other thing is, you'll see the lower panel has exactly the same data as the upper panel. It looks different, and that's because the vertical scale is different. In the lower panel, the scale for the vertical axis and the horizontal axis are the same. It's about 10 ohms for every, I don't know, whatever, centimeter and a half or something on my screen. And the lower panel is the way that traditional impedance spectroscopers always plot their data, even though it leads to this compressed spectrum, which violates every rule you were taught in grade 5 about how to plot a graph. You should not leave a whole bunch of white space in your graph. So you should change the scale so that you can actually see things and make a decent graph out of it. The reason traditional impedance spectroscopers like to plot this way is because an RC parallel circuit gives an impedance spectrum that's an exact half of a circle, a semicircle, so that it means the height of the circle would be 1/2 of its width if this were a half of a circle being plotted. And this portion you can see goes up to about 8 or 9, but if you had to make an estimate of its width, you would say it's about 30. So this is a flattened semicircle. And you can see that clearly if you plot things the traditional way. Here, you have to do a little bit of mental gymnastics to just realize, okay, this is 8 and this is 30. It's not a perfect semicircle, even though it might look more closer to a perfect semicircle. So we get into conversations with referees all the time because we plot our impedance spectra like panel A, and traditional impedance spectroscopers want panel B. All right, so now I need to explain to you what these cells are. All right. So I'm going to draw a picture of the cells on my document camera. Think you can see the document camera again? Is it true?
Yep.
Okay, so these are cells that look like this. Has metal. And it has a positive electrode. Has aluminum foil. Another positive electrode. Then a separator. And then it has a choice could be a negative electrode, or it could be a positive electrode. So I'm going to draw it as a positive electrode symmetric cell, so-called. And then it has another big piece of metal underneath. So this is a coin cell prepared from small pieces of electrodes taken from a pouch cell, double-sided electrodes taken from a pouch cell. And everything's full of electrolyte. So we would call this a double-sided positive symmetric cell. Okay. So what is the blocking and what is the non-blocking of these two cells? Blocking means assembled with fresh electrodes, both whatever, lithium MO2. So this is a trick we actually learned from Michael Metzger's group in Germany, where they do this type of stuff all the time. Non-blocking means one electrode is LiMO2 and the other is lithium X MO2. And when I talk about one electrode like this, one electrode is this and the other is that. So this would be, say, the black one. And this would be the blue one up above. So what's the difference between these two cells? The difference is if you try to transfer in the case where both electrodes are LiMO2, if you try to transfer lithium through the electrolyte, through the separator from one electrode to the other, you can't. You can't do it because if you try to remove lithium from one, which is full, that's okay. But put it into the other, which is full, you can't. It doesn't fit. So the transport of lithium from one electrode to the other is blocked. Can't happen. In the other case, where one electrode is full and the other one is partially empty, you can transfer from the full to the partially empty, and then you can transfer back again. So in that case, lithium can transport between the two electrodes here across the separator, back and forth, back and forth. So that's the difference between blocking and non-blocking.
Hey, Jeff.
Yeah.
You can also get a blocking cell set up using electrolytes that don't conduct lithium, correct?
Yes, you could do that. The reason that we're doing this is we're trying to understand what part of the impedance spectrum comes about because of the charge transfer from one electrode to the other, where you actually have to do charge transfer through a cathode electrolyte interface. So what you've done is everything else in the whole cell is the same. Whatever the heck is going on is going on. But you want to be able to identify what portion of the impedance spectrum is coming about because of the transfer. through the charge transfer interface that's happens in the non-blocking case compared to the blocking case. So let's go back and take a look. Any more questions about that? Just before I go back. So we'll just go back and look at that. Oh boy, where is it? I don't know. It's impossible to see. Is that my PowerPoint showing up for you?
Yep.
Yeah. So if you look at the blocking case, it's the red. There's an impedance spectrum there, and I don't want to worry about where the origin of the various features comes from in the red one. I just want to show you that when you allow charge transfer to occur, you get this extra component here, which was not there before, the black one, okay? So that you associate with a charge transfer impedance. And you can calculate what these little impedance spectra look like. And I'm going to do that at the beginning of next class. We'll just calculate impedance spectra for various combinations of RC parallel connected circuits to see what they look like, all right? But here's an example when the charge transfer resistance is set to be 10 ohms and the series resistance is set to be 1.5 ohms. You know, you get this shift of 1.5 ohms from the series electrolyte resistance and then the charge transfer resistance. So this is 10 ohms wide and it's 5 ohms high. So it's a perfect semicircle, right? And the experimentally measured spectra are squished. Like I mentioned, this is not a perfect semicircle. It's squished in the vertical direction. So why is that the case? That's where we'll start next day. We'll talk about why the experimental spectra are squished and what we do about it to try to model that. Yeah, so the reason I want to show you this graph on the left is to really convince you that the charge transfer part is a semicircle. Experimentally, it's a semicircle. Almost a semicircle, squished semicircle. Okay, any questions?
The height of that circle and the reason why they kind of give you trouble when you try to make the axes different, does that have to do with the open circuit potential?
No, has nothing to do with open circuit potential. They're just used to looking at impedance spectra that are plotted on equal axes. When you look at thousands of them, when they're plotted on equal axes, you say, oh, that's a perfect semicircle. Oh, that's a squished semicircle. But if it's a funny axis and you have to spend a few seconds mentally calibrating your brain to the axis length on the two axes, then it annoys people. So some people get annoyed because the graphs don't use the whole graph paper, and other people get annoyed because it's not equal axes. So you can't please everyone.
I would make a comment about the axis. So technically on the bottom graph, you can cut off you can limit the y-axis so that you'll, populate more of that room. But I think also the reason why traditional spectroscopic EIS people like the isometric axis is because you can see some of the features and they're not skewed by the change in the axis length. So like the 45-degree Warburg impedance and stuff like that. And in some cases, the semicircles, they might, if you use the top kind of axis, it might, make it look as if you have one semicircle, but actually if you do the isometric axis, you can see that you might be able to fit like more semicircles under it, stuff like that.
Yeah, Ron makes some good points here, which are all true. And it's, again, it comes down to, you know, I think the most important comment there is the fact the 45-degree angle for this low frequency part over here. It's what sometimes people want to see. If this is a 45-degree angle, it's indicative of diffusion-related processes. This is not 45 degrees. This is not 45 degrees. So there's some other stuff going on that I don't want to talk about because I don't know what it is. That's not the goal of showing you this particular figure.
Jeff,
Yeah.
if we compare this the charge transfer resistance from this EBS spectral with the equations you got, the several equations, so which part of the components corresponding to the semicircles here? Because when you have this when you have these equations, which part corresponding to the charge transfer resistance? The one with the capacitor. Okay.
Capacitor, resistor in parallel. Yeah, which is this.
I see. Thank you.
And we'll put all this into a spreadsheet next day, and you'll see how it works. Okay. All right. I didn't get very far today. It's probably going to take all of Wednesday to finish this, I guess. So we'll see. All right. See you all Wednesday.